Okay. So first of all, the presence of my laptop here is an optimistic statement that we will finish the theory and start implementing it. Let's see if it will happen. So I want to talk about compositions and Gaussians and compositions of Gaussians today. But let me first remind you that we constructed a map from homomorphisms between a polynomial ring in the variables in some finite set ZA into, two polynomials in two polynomials in variables corresponding to some finite set B into some funny set of power series. So this was the generating function morphism. So these are the generating, these are the power series with coefficients in due letters corresponding to the variables in A, and with coefficients, what did I say? Power series in variables with in the zeta A's with coefficients polynomials in the ZB's. And then we gave primarily two examples. So the generating function of Rij, where you think of Rij as the homomorphism from an empty set or from a polynomial ring on an empty set of variables to polynomials in four variables, xi, xj, pi, and pj's. So Rij becomes this expression, where from this point on, I will use capital T, uppercase T, to denote the exponential of lowercase t, just to make it easier to write. There is eta I, 1, okay, but 1 is just 1. By the way, if you want, you can write 1 as e to the 0. And we found the generating function of multiplication in the Heisenberg algebra. So that's a map from the tensor product of two polynomial rings into a polynomial ring. So it's a map from polynomials in four variables in xi, xj, pi, and pj into polynomials in two variables, xk and pk, and the generating function is written here, and we computed it last time. Now, what we really want to know is how to compose such thing, because if Rij indeed satisfies the Young-Baxter equation and all the other equations, and then all we need to do is to compose such things in order to compute the corresponding knot invariants. So we need to know how to compose such things. And so for that, first I will tell you a story about how to compose generating functions in general, and then I will note that both of these are in fact Gaussians, so the exponentials of quadratics. And then all I will care about is how to compose quadratics, or the exponentials of quadratics. And that will be the next thing to do. So first of all, how do you compose in general? So you see, there is a map from homomorphisms from Z8 into ZB times homomorphisms from polynomials in ZB into polynomials in ZC, there is a composition map into polynomials in, or homomorphisms between polynomials in the variables in ZA into polynomials in the variables in ZC. So this is power series of this kind. This will become power series in the zeta b's variables with coefficients, the ZC variables. So there ought to be a map from this tensor that into power series in the output variable, sorry, in the Greek input variables with coefficients which are the Latin output variables. And furthermore, I hope that this diagram will be commutative. By the way, even before telling you that, I mean, even before telling you what this map is, or what the corresponding composition map here is, I should tell you, I mean, I should put it in a sort of more general, bigger context, okay? So the fact that you compose such things means that there is some category in the background. So I don't know what should we call this category. Home HP. Okay? So here is a new category, HP. It stands for homomorphisms, homes between polynomials. I just invented the name. Okay? So HP is the category with objects, finite sets A, and morphisms. So the morphism from a finite set, morphisms from a finite set A to a finite set B is homomorphisms, linear homomorphisms, just vector space homomorphisms from polynomials in A into what am I doing? Sorry, I'm not concentrated. To polynomials in B. And there ought to be another category, gen, for generating functions, which is corresponding to the line down here. So this should be the category with objects the same. So finite sets, well, let's call them A, and the morphisms, so I suppose this is the morphisms in HP, this is the morphisms in gen. So the morphisms in gen between a finite set A and B should be the power series in the variables corresponding to zeta A's and zeta A's with coefficients the ZB's. So in this category obviously has identity morphisms. The identity morphisms here, we computed the identity morphism, right? It's E to the sum, so this is the identity of the object A, and this will be e to the sum over all lowercase a in A of zeta A ZA. And this one has a composition, and now I'm trying to understand this composition. Okay? The fact that it exists is obvious. We just have to find out what it is. It's obvious because these are isomorphisms. Why are they an isomorphism? Isomorphisms? Because I can go back. Right? So, if I know the generating series, and I want to know where does a monomial go, so I want to know what's the corresponding homomorphism, all I need is to look at the coefficient of the corresponding monomial in the zetas. So let me make it explicit. So suppose L is in the morphisms in the category HP between finite sets A and B. In other words, suppose L lives here. Okay, so I have an element L here. And suppose calligraphic L is the generating function of L. So it belongs to the morphisms in the category of generating functions between A and B. Now suppose I know L. How do I recover lowercase l? So suppose I want to compute G inverse of lowercase l, suppose I know calligraphic L, how do I recover uppercase L? So I want to compute G inverse of L on a polynomial P where, right, because G inverse is a map from polynomials to polynomials, so where P is a polynomial in the variables Z sub A's. Okay? So what do? I need to find the corresponding coefficient of this power series. And how do you find the nth coefficient of a power series? You differentiate it n times and substitute n is equal to 0. And substitute the variables to 0, so that you select only that coefficient you want. Okay? So this is equal to, you take the polynomial P, you replace every time you see a Z sub A in it, so every variable, you replace it by the differentiation with respect to the dual variable, the zeta A. You evaluate this differential operator on L, and then you substitute all the Z sub A's going to 0. Okay, this is standard. This is exactly how Taylor series work. I think there is a divide by n factorial in the formula, but I've divided already by n factorial in the definition of generating series, so I don't need to divide by n factorial here. Okay? Good. So once you have this, it's clear how to compose power series. Namely, suppose I have a power series here, let's call it calligraphic L, and a power series here, let's call it calligraphic M. How do you do calligraphic M? Wait. I don't know. Calligraphic M. I want to tell you what is L composed with M. So, you know, maybe I'll remind you that it's kind of nice to think of L as having its Greek letters on the left and Latin letters on the right, and likewise as M of having its Greek letters on the left and Latin letters on the right. So now, what is the composition? So the composition should have Greek letters corresponding to the to the inputs. Whatever inputs I put, I feed them into L. I get Latin letters. This should be the output that goes into M. But the output will be polynomials in the Latin letters. And how do I feed it into M? I use this formula. Namely, I differentiate M with respect to the dual letters of the Latin letters that appear here. Okay? So what I do is I take L, replace it, replace every Latin letter that I see on the output side. So in other words, every Z, Z sub B, I replace it by differentiation with respect to the dual Greek letter. Now, these Greek letters appear in M as the input variables, because M has Greek letters corresponding to the middle finite set. So I apply this to M. I kill all the remaining Greek letters. Oh, sorry, here I should have killed the Greek letters, not the Latin letters. I kill all the remaining Greek letters in the result, and that's it. That's the composition. Okay? Here's a different way. Here are a few other formulas for the same thing. So, a different formula is to say we multiply L by M. So we simply multiply them as power series. And you see, every time we see a zeta in, a z in L, so an output, we should feed it into the corresponding zeta in M. So we apply this bracket thing, where the bracket thing is defined by, so the bracket of z to the power n zeta to the power m is delta n m, in fact, multiplied by n factorial. So you see where n and m both belong to the natural numbers to the power b. So these are multi-indices. So whenever you see a monomial in the z's and a monomial in the zetas, if they match, you get n factorial, because that's what differentiation will give you, and otherwise you get 0. Now, the way I wrote it here is symmetric, and it corresponds to the fact that I could have written this in the opposite order. So I could have written this as m, in which you replace every Greek letter with differentiation with the corresponding Latin letter and apply it to L. So m subject to every zeta b goes to differentiation with respect to the corresponding Latin letter. This operator applied to L, and then you substitute zb is equal to 0. Okay? And there is yet another way to write it. Maybe, again, symmetric like this was symmetric. So I could look at the product of L and M and apply to it the differential operator e to the sum differentiate L with respect to its Latin letters and M with respect to its Greek letters. So apply to it the operator. Now, I didn't leave enough space. So dz sum over all b's of dzb d zeta b applied to L times M. So, and then substitute if anything remains, you kill it. So substitute all the Greek and all the Latin letters to 0. And in fact, there is yet another formula, but we will see it only next time. Or, I don't know, one of the next times. The way I like to think of it, so, you know what, here is yet another, not quite formula, but here is a way to think of it. So, I like to think of it as, so, L is a sum of monomials, and I will indicate monomials with like boxes where the inputs on the left are Greek letters and the outputs are Latin letters. So if I don't put any labels, this box stands for zeta to the 4 z cubed. Okay? Correspond, and likewise M is a similar thing, so it's a box with Greek letters on the left and Latin letters on the right. And if you want to compose them, what you do is you put them side by side. And you sum over, well, you turn these into differential operators and let them act on those. Okay? Which amounts to saying that each differential operator must pick a corresponding variable with the same name. So it's the sum of all matching, but provided you preserve the names. So you're only allowed to match, so you know, if this is Z1, Z2, Z1 again, so you're only allowed to match letters with their corresponding Greek letters, Latin letters with their corresponding Greek letters. Okay? So this is L composed with M. I lied to you in a small way in several of these formulas. Really, in a really small way. So you see, in this formula, there is no confusion. But in this formula, some of the Latin letters of M might interfere with the Latin letters of L. Right? So when I'm pairing Latin and Greek, by mistake, I may end up pairing a Latin output with which shouldn't have been paired. Likewise, the Greeks of L should not be paired with anything, but could be paired with some of the Greeks of M. Sorry, with some Latins. So this formula is true, assuming there are no interferences. So assuming, right, L went from A to B and M went from B to C. So assuming A intersect B is B intersect C is the empty set. Again, in this formula there are no issues, but in this formula, again, there may be interference between just names that are repeated for no reason. And so here I'm also making the same condition. So assuming A intersect B is B intersect C is the empty set. So basically no coincidences where a Latin letter here is by mistake regarded as belonging to here. Okay. Good. Example, yeah?
A quick, could you explain the notation, the bar zeta A goes to the delta of zeta A?
Where?
In the G inverse formula. P,
this?
Yeah. Yes.
So
the
P
letter
is a polynomial in the ZAs.
Yes.
You replace every ZA by differentiation with respect to zeta.
I see.
And then you apply it to L.
So the L we have, is it the L inside
yeah.
there or down there?
L, this is calligraphic L. It's
okay.
a power series, right? So this is a power series in the variables, a power series in the Greek letters in A with coefficients the Latin letters in B.
I see.
Okay? So if I differentiate it with respect to Greek letters, I only get Latin letters, which is how the output should be. Okay. Examples. So, I'll only do a silly example. So, let's compute 1 plus zeta1 z1 plus zeta2 zeta1 squared z1 squared composed with 1 plus, in fact, more or less with the same, zeta1 z2 plus zeta1 squared z2 squared. So first of all, what are these things? So this is a homomorphism that takes polynomials in Z1, right? Because the Greek letter appearing here is zeta1, which is dual to Z1. So this is a homomorphism from polynomials in Z1. The output letter is also Z1. So polynomials in Z1. Okay. This polynomial takes Z1 squared. So the term of zeta1 squared takes Z1 squared, is telling us where Z1 squared goes. So Z1 squared goes to Z1 squared. That's what it says here. So Z1 squared goes to Z1 squared. Nope, I lied to you. Because remember that in the generating functions you divide by n factorials. By n factorial. But here, so had it been what I wrote here, it should have been 1/2. But there isn't a 1/2, so really this takes Z1 squared to Z1 squared. Likewise, it takes Z1 to Z1, and it takes 1 to 1, and all other monomials go to 0. Okay, a rather stupid polynomial, a rather stupid homomorphism. Likewise, this one, except here the inputs are Z1s, and the outputs are Z2. So this is a homomorphism from polynomials in Z1 into polynomials in Z2. And it's the morphism that takes 1 to 1, Z1 to Z2, and Z1 squared to twice Z2 squared. Now, let's compose them. So, the composition is, you write, well, 1 remains 1. Zeta1s remain zeta1. Z1 becomes D to D zeta1. You know what, sorry, my convention is to write it as partial subscript zeta1 plus zeta1 squared partial with respect to zeta1 squared. So I take this differential operator and I apply it to 1 plus zeta1 plus zeta1 z2 plus zeta1 squared z2 squared. And then I evaluate all of this at oops, sorry, I was wrong. I evaluate this at Greek letters equal to 0, but I got myself wrong, really. So I want the Greek letters here to be set to 0. I want the perfect. I want the matching of the differentiations with the monomials to work here. These Greek letters are irrelevant. Okay? I mean, they're different. So in fact, sorry, all of these, I was wrong. All of these were under this assumption. Yeah, I failed to notice that. Sorry, when you evaluate, you really mean it's these Greek letters that I want to kill, not those. So how do we do that? So one way to do it is to temporarily put bars on top of the letters. So the letters that I want to compose, I will put bars on top of them. So this will be zeta bar, and these will be zeta bars, and only the barred letters I want to send to 0. Okay? So really, I take this polynomial, make the substitution, z goes to dz bar, and I take this polynomial and take the coefficients, the substitution, zeta goes to zeta bar, and then apply the same formula there with the temporary names. Okay, but now I can compute. So, if I multiply the 1 with any one of these, and then substitute zeta bar equal to 0, this dies, this dies, the only thing that stays is 1. So I get 1. dz bar kills this term, turns this term to 1, so I'll get zeta 1 z2 bar, zeta 1 z2 bar, zeta 1 z2, and if I apply this to this, the differentiation, I'm differentiating with respect to zeta bar, a zeta bar squared, so I still have a zeta bar too much, and I substitute zeta bar equals 0, so this dies. And then the last term is, if I apply this differential operator to here, I get 0. If I apply it to here, I get 0 because I'm differentiating twice and I only have 1 zeta bar. If I apply it to this, I get 2. So I get twice, and then the differentiation and the barred variable disappears, and I'm left with zeta 1 squared, z2 squared. And this corresponds to the morphism, which takes 1 to 1, z1 to z2, and z1 squared to 4z2. Because had it been the identity, it would have been a half. And if I have a 2, it means that I'm 4 times bigger. But that's exactly the composition of these two morphisms. Sorry, that was silly, but okay. Am I going too slow? Am I going... I don't know, I mean, okay. Okay, now comes the big jump. I don't know if I have time for it though. Well, let's try. So, I have my two categories. Right, so I have HP, and I have G, which is a morphism, which is a functor, sorry, it's a functor into the category gen. And what I want to tell you is that the category gen has a subcategory, GDO, and GDO is the subcategory that contains all of these things, and we will always work, namely the Gaussians, and we will always work inside it. So GDO is the category of Gaussian differential operators, and the name is because the elements are Gaussians, but they compose like differential operators. You make substitutions and compose like differential operators. So what is GDO? So GDO is the category with objects are finite sets, and the morphisms between a finite set A and a finite set B are elements of, well, I've erased it, but elements of this power series polynomial ring, which can be written in the form omega times the exponential of Q, where omega is a scalar, so just a number, or if we work over power series in some other variables, an element of this power series ring, okay? And Q is a quadratic. So Q is a quadratic, but what does it mean? So I have three types of variables. Sorry, two types of variables, Greek and Latin. So I have three types of quadratic, Greek, Greek-Latin, and Latin-Latin. So it's equal to 1/2 times the summation over I and j inside the set A of, so A are the inputs, so these are Greek letters. So these are zeta I, zeta j. That's the quadratic. And then I'm allowed to take any coefficient I want. Let's call it f. Okay? Plus a summation over, notice that there is a 1/2 here and there isn't a 1/2 here. Plus a summation over I in A, J in B. So these are the mixed quadratics, so the mixed monomials. So I is Greek, J is Latin. So this is zeta I, Z, J, and I'll call the coefficient AEIJ. And finally, a summation over I and J, both Latin, of, with a 1/2, of, so this is Latin, so ZI, ZJ, and I'll call the coefficient GIJ, where all of these things, the Fij, the Eij, and the Gij are scalars. So again, genuine scalars, namely numbers, rational numbers, or if we're working over some power series ring, then elements of that power series ring. Okay. Well, if it's a category, it should have identity maps and compositions. So the identity maps are, as we have written before, and they are quadratic. So the identity of the object A is 1 times e to the sum zeta A ZA. So the scalar part is 1, and then we have the exponential of a quadratic, and the quadratic has only Greek Latin terms. That's a fair thing. But now I have to tell you how to compose. Okay? So I have to tell you, well, how to compose two such things. Compositions. There's no way I can fit it in the 3 minutes that we have left, so I'll only tell you that if we succeed, we won. So won, I mean a battle, not the war. I mean we've done something great. Why? Well, first of all, it means that we will know how to compose these things and get an invariant. Okay? But even better, it's a super easily computable invariant. Because you see, the Heisenberg algebra was infinite dimensional. That seems impossible to compute with. We switch to maps between polynomial rings, that's still infinite dimensional. So, like this category is still unmanageable. It's in fact uncountably dimensional. Okay? However, this category is tiny. So this is tiny. Why tiny? Because how much information is there in a morphism from A to B? Well, a scalar, one scalar, and then 3 matrices of scalars. So basically there are as many scalars as roughly the square of the size of A and B. Right? Because, okay? Because we have double summations over A and B. Okay? So this is, what does a tiny mean? It means quadratic dimensional. So, if you have a knot with 70 crossings, with 100 crossings, you will only ever need to work with at most 100 copies of the Heisenberg algebra, maybe 200 copies. Okay? Each one involves 2 variables, so 400 variables. Square 400, you get 1600 dimensional spaces. 1600 dimensional spaces is nothing. Okay, I mean, so if only we found how to compose these things, we would be managing tiny things. So we have a chance of working with huge knots. Yeah, so I'll see you next time. You can turn it off.